Hi, welcome to this video, and in this video we've titled it the Randle-Sevcik Equation, a Python simulation. So we will finish with a Python simulation of the Randle-Sevcik Equation, but there will be three main parts to this, and we're going to sort of hopefully build up chapters and pages, even though in video format, to sort of bring all this together. But this video is really part of a kind of a new movement that at ZP that we're really kind of keen to be part of. If you find the contents of this interesting, do like and do subscribe, because there will be other videos like this, especially if we get some feedback that people actually like this. Really what's going to happen here is we'll talk about theory, we'll do an experiment, and we'll do a Python simulation of that theory as well. So as I say, the theory or the experiment we'll be doing tonight is cyclic voltammetry. I have a potentiostat in front of me, so I really like practical science. There's a theory that describes voltammetry, and then at least with electrochemistry, it's actually quite straightforward in this modern age to actually, potentiostats are not necessarily super big anymore, super complicated. I can set this experiment up in possibly 5 seconds. So I've just put the electrode in there, no cabling required, it does match up. I can close that, and that's attached. I've got some solutions here, and I will add some solutions very shortly, solution to that electrode in a minute. With that said, so there's three main parts for this evening. There's theory, there's experimentation, and then there's simulation. And I really like the simulation because the theory essentially tells us what we should expect. The experiment gives us the results, and the simulation kind of tells us, helps to that glue between the theory and the experimentation. And also the simulation then, for the experiments that we don't do, we can predict, as long as the theory is sound, what other experiments will do. So it's a very efficient way of scoping out the experimental landscape. But of course, you still have to have experimentation just to kind of put in some of the data points. Now, I'm not going to make a big point of it this evening, but I'm only really looking at one feature of the cyclic voltammogram, and that's its peak current. If for a well-behaved reversible system, the peak current is of a voltammogram is proportional to the square root of the scan rate. Now this is summarized in the Randle-Sevcik equation, and I'll dig into that just in the next few slides. But I am very interested in the main theme of this evening just being this connection between theory, experimentation, and simulation. So this kind of triad of the three parts here. So the theory, as I said, I'm not going to dig in too deeply because in fact we have quite a long video on cyclic voltammetry. I think it's had something like 40,000 views on it. So the theory of cyclic voltammetry can be drawn there. I just want to pull out one particular aspect. By the way, if I sort of reference something and you don't, I will put a link to the video underneath as well. So there's only one feature of the cyclic voltammogram that we're going to simulate tonight, and that's the peak height. And the peak height or peak current is proportional to the square root of voltammetry. Anyone who studied electrochemistry, this is kind of one of the first things that is taught. It's fair to argue, actually, this is becoming dated, which is a bit ironic for me doing a video on something that's becoming dated. Now, why do I say that? Well, at least in my world of electroanalytical chemistry, we're getting better methodologies, like square wave voltammetry, for example, is another voltammetry which is often very good for doing sensor and assay development. And by the way, I could do a video on that, and the equations are pretty similar. But that said, this is more kind of there's more literature out there on the Randle-Sevcik equation, so it's not a bad place to start. And it says that the peak current is proportional to the square root of scan rate. And you'll often see, in papers or in textbooks where they talk about current versus the square root of scan rate, and they'll kind of plot the peak current for something like the oxidation of ferrocyanide to ferricyanide, and then they'll put a sort of line through there, and that line is characterized by the Randle-Sevcik equation, which I have here. Now, I'll do a quick experiment in a minute, but I just want to sort of talk through what we're going to do. So I've got the potentiostat here, the sensor or potentiostat. I do have a screen printed electrode as well. I've got my 501 carbon electrodes. These just make for a nice, quick, easy to set up demonstration. We have an app on our phone. The app, by the way, is it's called Sense It All. It is downloadable from the Google Play Store and the Apple App Store. That said, it's not much use to you unless you've got the device, because they make Bluetooth connection with each other. It's basically a way of driving the potentiostat. But anyway, I can scan the QR code on that. It'll put into cyclic voltammetry mode, even though we do have EIS, square wave voltammetry, linear sweep voltammetry, OCP, and amperometry also on the potentiostat as well. I've already plugged in the screen printed electrode. That's really quite quick, no cabling, not even a slot. I'll put 50 microliters drop onto the working electrode, counter electrode, and reference electrode of the I'll just do that now, in fact, of the screen printed electrode. I'll hit go. When I hit go on the app will then tell this potentiostat essentially what to do. The potentiostat will run the voltammetry, and you'll probably see that appearing on my phone in real time. It'll send the data to a cloud system that we call Julie, and then I'll be able to view the data up in the cloud system. So the theory bit is we're going to do cyclic voltammetry. The peak height of cyclic voltammetry is proportional to a series of constants. Some of those constants, a series of parameters. Some of those parameters are discussing the area of the working electrode, for example, and some of those parameters are proportional to the concentration of the analyte, which in my case is ferricyanide, and its properties like diffusional coefficient. So that will go up to the cloud system, and I'll be able to view it there. Now I say here I'll do an experiment, and this is just me a quick way of reminding myself to actually do the experiment. So if I just come to what I like about electrochemistry as well is it can be quite quick and clean. So I have some solution here. This is 5 millimolar ferricyanide. I've put a 50 microliter drop on the end of there. I can just go continue here. I've got my settings. These are kind of quite classic. Minus 200 millivolts starting potential, 600 millivolt end potential, scan rate 100 millivolts. I'm just doing that because it's much quicker. Just one scan. My current range is 100 microamps. I'll start my experiment, which I am doing. And now the voltammogram is it's actually running it, and I'm seeing the current kind of effectively appear in real time. That should only take a few seconds because the scan rate is set to be deliberately quite high, because it makes for a much more, let's say, interesting. And then it says upload complete. So the data, in fact, has actually gone to the cloud. So I'm just going to navigate here, and I will share my screen here. Right, okay, so I've done the experiment. I'll just do a quick refresh here, and I could just see some new data just jumped up here, and that will be my latest, let's say, experiment. I can just zoom in and have a quick look at it here, so I can see my cyclic voltammogram that I've just recorded, and that was at 100 millivolts per second. I can just kind of compare it against one that I would have done earlier on. It says 10, so that's probably 10 millivolts. Here's my 100, so that's 100. I can just combine these two. It'll combine into a single report. I'm just going to turn on. I want to see that, and then I can have a quick look. So it's just loading those up. So I'm just going to zoom in a little bit. I could have zoomed in a bit better than that, but I can see here my 10 millivolts. So the solution's the same between these two experiments, except one of them was done at 10 and the other one was done at 100. Just going to try something for a second. No, that doesn't work very well. Oh yeah, that did work quite well. Okay, so somebody, first of all, right, I'm trying to bring together three aspects here. The theory is that the peak current in a cyclic voltammogram for a reversible system should be proportional to the square root of the scan rate. You can see here that it is proportional to the scan rate because I've got one at 10 and one at 100. Then I wanted to do the experiment itself, so that's the experiment, and then I want to kind of get to the last bit really, which is really interesting to me, which is then starting to bring it all together, because I feel like you can bring it all together then through the kind of simulation. So the code I will show you is also linked. I've got a URL here, but I'll put the URL or link rather underneath the video as well. So we've got this Randle-Sevcik equation. It's classic. It's very robust because it's been used for sort of many years, and so it's kind of been through many filters, and it's been shown to kind of hold up. And I have some Python code here, and in the Python code, I'm just going to kind of zoom in on this particular area, because you can basically go in there and kind of edit these numbers or these parameters, or these variables rather. So n means the number of electrons. Sorry, first of all, I should start here. The Randle-Sevcik constant is 2.69, and it's basically a combination of Rydberg constant, temperature, and Faraday constant. So it's a bit lazy of me not to have shown you where that 2.69 times 10 to the 5 actually comes from, but it's a combination of the Faraday constant, the Rydberg constant, the temperature, which is 298. So that's where in the Randle-Sevcik equation, you can find that in the code, which I say is accessible. The current is also proportional to the number of electrons to the power of 3/2. You can because the experiment I just did was the oxidation and reduction of ferricyanide. The number of electrons is actually 1. Because I was doing it on one of our 501. Sorry, and there's a picture of the ferricyanide there. The picture doesn't add a lot of value, but it's just to say that this is ferricyanide. It's at 5 millimolar concentration, which will become useful in a minute, because you'll see I've also got that in the code as well. The area of the electrodes, because I was using one of our 501s, I know what the area of the electrode is, so I've also put that into the code as well. So it's the area of this carbon disc here in the center of that image. The diffusion coefficient, so I've put the diffusion coefficient in for ferricyanide, 6 times 10 to the minus 6. I know it's the concentration, it's 5 millimolar, so I put in 5 times 10 to the minus 3 into the code as well. I do have an extra term in here, which is blocking. This is just something where I was interested in. If I block the electrode, the signal should decrease proportional to the amount of blocking, but I haven't done any blocking in this particular experiment. That's not, strictly speaking, in the Randle-Sevcik equation, but I've just added it in there in case I kind of was doing some additional modifications of the electrode. Now, what that Randle-Sevcik simulation will give out is actually this. So if I look up here, I have a sort of logarithmic scale of scan rate and peak current. And so if I have a scan rate of 10 millivolts, I'll get an approximate current of approximately 10.5 microamps. So I'll just go to the code. As I say, you can actually download this code anyway, and you can play with it. But so these parameters here. Now I realize I've got more parameters in here than you actually need, because the only ones that are really kind of, the equation itself is down here, and I can see it's using the Randle-Sevcik constant, which is here. It's using number of electrons, which is here. It's using effective area, but the effective area is the area times the blocking, but because I've put the blocking as 0, it's just the area of electrode. And the diffusion coefficient for ferricyanide, which is 6 times 10 to minus 6 in this particular case, the square root of it. The concentration of ferricyanide, which is 5 millimolar, and I didn't want it in amps, so I've sort of got it printing out in microamps. The easiest way to kind of see the effects, if I just make that 10 now, and then run this, it will have scaled. It just scaled everything because I just put in 10. I'll just put that back to 1. 1, and then I can run it, and it will change the scaling on that again, because now it's only 1 electron. So I just want to go back to my slides and just kind of say, okay, so what we were trying to achieve this evening was to sort of say there's always been theory, and there's always been experimentation, but now it's kind of nice now that we're able to have our theory, do our experiments, and then with Python we can actually see, we can explore almost experimental landscape. What will be the current at this particular scan rate just by having a Python simulation in this particular case for the Randle-Sevcik equation. Now, as I say, this is kind of a first of a potentially a new series from Zimmer and Peacock on the adoption or integration of Python into electrochemical biosensor research. So if you've got any suggestions, questions, etc., be super happy to hear them. Links to the code, the Python code for example, will also be underneath the video, and I'm happy to receive feedback. Okay, thanks very much.